we're starting a new section of the course, and this section has to do with the fact that now that we've seen the parts of a cell, the cell needs to do things with those parts. It needs to bring in energy for itself and molecules and do things to those molecules to provide itself with fuel. And I've been watching, just to kind of give you a little bit of context, I've been watching this reality series called Alone on the History Channel, and the premise of the show is that people are placed in a wild environment this season. They're in Patagonia. They're all by themselves. They have a few tools, but they have no food. And so they are out there all alone in the wild, and they have to provide food for themselves and shelter for themselves. And the person who can stay out there the longest wins $500,000. So watching this show has really impressed on me how critical it is to get food. You know, we take that for advantage. We take that as kind of a given in our society. For most of us, at least, getting food is not a problem, and we don't spend all day thinking about it. But these people out in the middle of Patagonia, that's all they do. All they do is think about, how can I get food today? They're fishing, they're gathering berries, they're eating leaves, they're trying to trap animals. They are consumed all day long with how to get enough food. And that's a problem that cells face. How can they get enough fuel to drive all the reactions that keep them alive? So that's the topic that we're going to be looking at over the next several lectures. And now I'm going to, having kind of set the stage a little bit, I'm going to try and return back to my slides because I want to start walking you through some of the concepts that we need to cover. So let's see if that works. Yes. So, Fong, can you see the slide that says tryptophan? Okay, good. So before we talk about this particular reaction, I want to say a little bit about a bigger concept, and that concept is, we're going to just call it metabolism. And metabolism is the totality of all the chemical reactions that take place in a cell. All the stuff they take in, all the things they do to those materials, all the chemical reactions that happen to those materials. And we can think of metabolism on a really tiny scale if you look at this image right here. So what I'm showing you is a series of small steps. We're taking a molecule. This is an amino acid, tryptophan, and we're going to change it into a slightly different molecule called hydroxytryptophan. It's just a derivative of that amino acid. And in the second step, we're going to convert it to a neurotransmitter known as serotonin. So those of you that are interested in neuroscience, this is a really important neurotransmitter. And you can see that we can make it from an amino acid in 2 short steps. So in metabolism, things happen in series, step by step. And so we can think of this as a very short metabolic pathway. And we're going to be looking at some metabolic pathways that are more complicated than this, but this is one that will get you started. We can divide up all the metabolic pathways into basically 2 big categories. So the first category is the category of catabolic pathways. And catabolic pathways are the ones that break down complex molecules into simpler ones. And usually that takes place with the release of energy. Okay? And the way I try to remember this, when I was an undergrad, I kept getting catabolic and anabolic confused all the time. So I don't know if this will work for you, but the way I remember the difference is catabolic is breaking down, and when I think of breaking down, I think of catastrophes. So the catabolic pathway, or any of the pathways that fall into this category, are pathways that break complex things down into simpler ones, and that usually happens with the release of energy. So, you know, a catastrophe kind of mentally connects that for me. And the other major metabolic category is that of anabolic pathways, and those take simpler molecules and build more complex ones from them, usually by consuming some energy. Oops. I know. So you can see these two sort of are opposites of each other. And you'll notice that a common theme here is whether energy overall is released or whether energy overall is consumed. And so we really need to get a handle on energy then, because it's going to play an important part of how cells go through metabolism. So I need to lay some groundwork for you, ways that people think about energy. And you might be familiar with this idea that energy can take different forms. So we're just going to talk about a couple of forms. And the first form that I've listed here for you is kinetic energy. That's the energy that's associated with the motion of objects. So water flowing, rocks crashing down on something, that's kinetic motion. And a subtype of kinetic motion we could describe as the thermal energy of atoms. So you know that atoms are bumping around due to their sort of own thermal energy, and that motion we can think of as kinetic energy. The second big category of energy is potential energy. This was the one that often is a little trickier to get a handle on, but basically this is energy possessed because of location or because of structure. So if I climb up to the top of a ladder, there's energy inherent in the fact that I'm elevated, because if I jump off that ladder, the fact of my body falling from a height delivers energy to the ground when I land on it. And a subtype of potential energy is chemical energy, the energy contained in the arrangement of atoms in a molecule. And so we're going to be kind of thinking of all these different kinds of or forms of energy as we progress through the sequence of ideas that I'm going to lay out for you. So before I go further, I just want to, let's see if I can bring it back to me for a moment. So one of the things that is sometimes kind of anti-intuitive, at least to my way of thinking, for biologists, is that a lot of the terminology that's associated with energy comes out of a very specific historical period. So in the 1700s and the 1800s, humans for the first time were inventing ways to power work that didn't rely on their own muscles or the muscles of animals. So they were building steam engines, and they were building electrical engines, and they were building internal combustion engines. And they became very interested in what were the physical laws that governed just how efficient these engines could be. So over the course of developing, practical engines and trying to understand what ruled their efficiency. Some terms were developed that I think sometimes seem a little foreign to biologists, and I think it's because they rose up out of engineering. People think of thought as engineers do. So, with that in mind, I'll try to kind of interpret these ideas from a biologist's perspective. So, let me get back to my screen. So let's go here. So first, some terminology that comes out of this sort of engineering way of thinking. So the first thing to define for you is what we mean by a system. So a system is just an object that can interact with energy in some way. So that's pretty simple. And an open system is one where here, I'll type it out for you. An open system is one where the object can exchange energy with its surroundings. And so if we look at the car down here, this is an object, and if we start it up and we start driving it around, it's going to be exchanging energy with the surroundings. The wheels are going to turn, and that's going to propel the car forward. And so we can think of the car as an open system. And then the third definition here that we need to share is what we mean by a universe. And what we mean by that is the system plus the surroundings. Okay? So our open system is the car. It can exchange energy with its surroundings, and the universe is the car plus everything around it. All right. So that leads to the next idea, which is that we can think of two physical laws that are going to influence how energy moves. That's all that thermodynamics means, is energy movement. And the first law, this one I think is pretty easy to kind of get your head around. And it just, all it says is that energy is neither created nor destroyed. It can only be transformed or transferred. So we can't make new energy. We can only take energy that already exists, and we can change it into different forms. We can change from kinetic energy to chemical energy to potential energy. We can move it through different forms, but we can never make more, and we can never destroy it. And to me, that seems pretty intuitive. So I hope that's intuitive for you. The second law, that's the one that's a little bit trickier for people to understand. And so let's first say what it is, and then we'll develop it a little bit. So the second law says that every time we transfer or transform, some amount of it, some portion of that energy is going to become unusable. And by unusable, what I mean is it'll be escaping in a way that means we can't use it to do the work we want. So we can elaborate a little bit here. Can't be used to do work. Now, this idea that every time you transfer energy from one object to another, or every time you transform it from one form to another, that comes from this guy, Nicolas Sadi-Carnot. And I would guess none of you have ever heard of Nicolas Sadi-Carnot. He was a soldier in the French Army in the early 1800s. Really smart guy, and he published his ideas about energy when he was only 28 years old, which may seem old to you guys, but actually that's pretty young for such sort of innovative thinking. And sadly, he died of cholera just a few years later, so he might have become a really brilliant scientist, but he died before he could do more than just publish this Reflections on the Motive Power of Fire. So his idea, he first described this idea that when energy is transferred, some will always be lost in terms of not being able to use it to do work. And a number of people around this time and a little bit later took his ideas and fleshed them out and further developed them. And one really important person who came after Sadi Carnot was this guy, Willard Gibbs. And as it turns out, Gibbs was actually a native of Connecticut. And he took a lot of these ideas that were swirling around the building of engines and understanding the efficiency of engines, and he linked together ideas about total energy and unusable energy and energy available for work, and he put them all together into an equation, which we still rely on today. And so we're going to talk about Gibbs' equation. So what he did was he defined the energy available to do work. We're going to call it G, and something called the total energy in the system, we're going to call it H, and then this concept of unusable energy, which we're going to call S. And in fact, the people working in this area, developing these ideas, used S to stand for this unusable energy that's lost to honor Sadi Carnot. So the S stands for Sadi Carnot. And another term that people use for this is entropy. So you might have heard of entropy before. And then the last component of this that is important is the temperature of the system. So I'm going to try to give you a concrete way of thinking about it, and we're going to use my car. So I drew this little picture of my car, and the total energy in the system of my car is, we can think of that as all the gas in the gas tank. It's all the energy in my car as a system. And if I turn on the key and I start up the engine, pretty soon the engine block's going to heat up, and some of that heat's going to be transferred to the hood and the air molecules around the hood. And so, you know, when you have a car running for a while, you can see the heat waves rising up off the hood of the car. So you know you're heating the air around the vehicle. And also there's going to be some exhaust coming out, and that exhaust is hot also. So just intuitively we know when we start driving a car, we're going to be losing some energy from that gasoline in the tank to an unusable form. The air that's being heated, the hot exhaust that's being expelled. So that's going to represent the entropy of the system, the unusable energy. We can't use it to do work, to drive the car forward. So if we take the total energy in the system, the gas, and we subtract out what we're losing to entropy, what's left is the energy that can drive the car forward, that can turn the wheels and move the car through space. And then, of course, the temperature. I think intuitively it makes sense that if it's really, really cold out, that should have an effect on this system. If it's really, really hot out, that should have an effect on this system. So that's something we probably need to take into consideration. We're going to try to put this all together in a formula. So this is the equation that Gibbs came up with, and so I need to explain a little bit about some of these symbols. The delta, the triangle, that is a symbol that's used a lot in the sciences to mean change over time. And in a way, that kind of makes sense, right? Because we're not just looking at a static system. We're not just looking at my car sitting in the driveway. What we want to know is if I drive my car from my house in Manchester all the way into Hartford, I'm going to be using up gas. It's going to be heating the air around it all the time. So what's really more important to us is not a static moment in time, but what happens to the system as time progresses. So we're going to have a change in the energy available to do work, over time. So let's break that down step by step. So the change in total energy over time is the drop in the gas. So if we look at my gas tank, I start in Manchester, the tank is full. By the time we get to Hartford, I've used up some gas, right? So we've had a change in the total energy available. That's pretty easy to get our head around. And while I'm driving from Manchester to Hartford, I'm heating up the air around the car. The hot exhaust is being expelled. There's probably some friction between the tires and the road. So a certain portion of that energy is being lost to the surrounding system, and that's the delta S, or the change in entropy. And then lastly, what remains is the change in energy available to do work, to move the car forward. That's the delta G. And this is the thing. This is what we really care about. How much energy do we have to do work? So if we think about this, naturally people like to quantify things, and so we could actually graph this. So I'm going to show you what the graph looks like. The delta G, or free energy, that I have when I'm starting in Manchester, and the delta G, or free energy, that I have once I reach Hartford, there's a difference, right? It changes over the time I'm driving. I'm releasing that energy. It's driving the car forward. And so this difference here in the amount of energy that I started with, this energy that was released to drive the car forward, is exiting the system. And so we say that the change in delta G is negative. It's just a convention of the way the engineers thought about this. So another term for this kind of scenario is that the whole system is exergonic. Energy is being released or exiting. We say the delta G has a negative value and the system is exergonic. So I'm going to pause here for a second, Fong, and if anybody has questions, I can try to address them before I go forward. No? Okay. We're good so far? All right. So we can make this little graph. We can show that the delta G changes over time, and I've just shown you that that change has been defined as a negative change. Energy is released, so delta G is 0. Now, we can take this example, the one of my car, and we can think about it in terms of chemical reactions. So I already introduced you to the idea of ATP as a high-energy molecule, and I showed you its structure. It looks like this. And this particular molecule, you can see all these phosphates, right? 1, 2, 3, they're all close together. All these negative charges are close together. So that's one reason that ATP contains a lot of energy inherent in its structure. So remember, I said one form of potential energy is the energy inherent in the structure of something. So ATP contains a lot of energy because of these phosphate groups, all right next to each other. And if we break them apart, that releases energy. We can see that here. This is just in simple symbolic form. Here's the 3 phosphate groups. We can split this with a hydrolysis reaction. And when we do that, one of these phosphates is taken away and energy is released. And we can look at this in a little more detail here. Shows you a little more of the structure. And when that reaction takes place, we can measure it, and it has a delta G value of minus 7.3 kilocalories per mole. So this is just a unit of energy measurement. So you can see it's a negative value because that energy is released. Holy cow. The wind just went crazy. Sorry. So we can graph the progress of this reaction just as I graphed the progress of driving my car into Hartford, and it could look something like this. So the y-axis is the free energy in the system, the delta P, and we're starting off with a certain amount of that energy inherent in the bonds of the reactants. In the example I gave you, the reactant was ATP. And then the reaction took place, releasing some energy and yielding products that are lower on that energy scale. So, right, here's our products. We've got a phosphate group that's released, a hydrogen ion that's released. We've got now ADP, adenosine diphosphate. So those are our products. And we can graph the whole thing like this, where the x-axis now is progress of the reaction, or essentially a change over time. And the difference between these two is the amount of energy that was released. So because the energy is released or exits, it's an exergonic reaction. So now what I've just shown you is taking a system, sort of a macro scale system with the car, and showing you that it can work with chemicals too. Now, sometimes a cell needs a reaction to take place that's not exergonic. And here's just a reaction like that. So what the slide is showing you is not the actual chemical structure of glutamic acid, but it's just showing you as in its symbolic form. So you could take glutamic acid, which is an amino acid, and ammonia, and you can combine them to create a second kind of amino acid known as glutamine. But that reaction, you can see now, has a positive delta G. That means we have to put energy in to make this happen. And because we have to put energy in to make it happen, it's called endergonic. Energy has to come in for the reaction to go, and the delta G is positive. And if we graph that energy, you can see it looks a little bit like the other graph, except now the situation is reversed. Again, the y-axis is the free energy that we're measuring. We're starting out with reactants that have a lower free energy. We're putting energy into the system and creating products that now have more energy. We have to put energy into the system to make it happen, and so the delta G is positive. So that's an endergonic reaction. Questions so far? Nope? Okay. Zipping right along. So, how do we make that reaction that requires the input of energy go? Well, one little trick is we could couple it to a reaction that has a negative delta G. So I've already shown you this one, right? Here's the hydrolysis of ATP. It's got a negative delta G. So we can put these two together. Here's the reaction we want to drive, glutamic acid and ammonia to create glutamine. And here's the reaction that couples those two things together. We can take ATP and react it with glutamic acid. And you recall from the previous slide that when we hydrolyze ATP, it loses the phosphate. And in this case, it creates an intermediate where the phosphate is tagged on to the glutamic acid, yielding ADP. And so now we've conferred energy here to the glutamic acid. And we bring in the ammonia, and now we have sufficient energy to drive this part of the reaction and create the glutamine. So the overall result is the molecule we want to make, and then these two products. Right. So let's do the math. We know that to create the glutamine, we need to have positive 3.4 kilocalories per mole. And we know if we take advantage of the ATP hydrolysis reaction, we have a minus 7.3 kilocalories per mole. So if we put those two together, you can see overall the net delta G is a minus 3.9. That's still negative. So if we do these two reactions together, they will go. They will run. Yay, we can make glutamine. And I think this is just another way of looking at it that I thought was maybe a little more cluttered. But overall, what's key is to make this happen, we need to have a delta G that's negative to make it be an exergonic reaction. Okay. So if everybody's good so far, and I'm happy to take a question if your head is swirling and you need to think for a minute, or if you want to ask me something. Sounds like no. Okay. Now I need to I'm going to return you to looking at me for a minute. So that reaction, when a delta G is negative, that means the reaction is what's described as spontaneous, right? So in this context, spontaneous means something very specific. It means that the reaction will go forward without the addition of extra energy. It does not mean that the reaction will go fast. And so the way you can think about it is, if you imagine a glacier, you guys probably know, glaciers are slowly, they're sliding down into the ocean, and it's spontaneous. Nobody's putting energy in for that movement to happen, but it's really, really slow, right? So there's a case where you've got a spontaneous thing happening that's very slow. And so exergonic reactions don't need you to add energy to them for them to happen, but they may happen on the slow side. All right, so I'm going to go back to slides now. I think, yeah, here we go. How can we help chemical reactions go faster, right? So it may be that ATP will hydrolyze to ADP without us putting energy into the system, but it might take a while for that reaction to initiate. And you can think about my car, for example. The gas is in the tank, but if I don't turn on the engine, if I don't spark that first combustion event in the engine, it will just sit there. So we need a way to cause these reactions to initiate, I guess, is one way you could think about it. And that's where this idea of enzymes comes in. So today's Thursday. I think a lot of you have had lab already this week. Some of you that have lab this afternoon won't have had this yet. But in lab, you're working with proteins that act as catalysts, that act as enzymes that help reactions speed up. And here's how they do it. So you can see this little lump here is just a simplified drawing of a protein. And it's got this little cavity. And into that cavity, these two molecules fit very nicely. See how comfy they are, nestled in there in that cavity. And when they nestle into place, the enzyme, the protein, is able to position them just perfectly next to each other so that they are in exactly the right relationship to each other for that chemical reaction to happen easily. And it may be that the protein or the enzyme creates a little torque. Maybe it twists them in relation to each other a little bit. And that little twist or torque or positioning uniquely positions those molecules so that we can initiate the reaction and it can go faster. So what an enzyme will do is not make a reaction happen that cannot happen on its own. What an enzyme will do is will make the reaction happen a little more quickly. And here you can see this whole thing with words added to it. So the idea that an enzyme can make a reaction happen more quickly, if we go back to, hang on a sec, let's see, this slide. We know this can go forward, but what is not shown here is between this position and the products, between the reactants and the products, there's like a transition state where there's just this little hump of energy that needs to, the system needs to get over before this can proceed forward. And that's what the enzymes are helping you to do, right? So they are sort of creating the most ideal arrangement of the reactants so that they can proceed through quickly, and this can happen in a faster way than it would if we just sat around and waited for the reactants to over time bump into each other in just the right way so the reaction can happen. All right, so let me pause here and see if there are any questions. Nope, nobody wants. Boy, is there anybody in the room? All right. Okay. So if we are good with those ideas, then I've basically accomplished what I hoped I could today. I know it's a little early, but I was mainly worried about getting you through all the thermodynamics and the ideas that now we're going to apply these rules of thermodynamics to chemical reactions so that enzymes can help us make those reactions go more quickly. So if you have no questions, that's all I was hoping to get through today with you. So we're good? Okay. All right. Go stay warm. Okay, Fong. I'm gonna check out, and you can do that too. And if you would be sure to turn off the projector, that will save the projector a little bit. Thanks. Okay, thank you very much for your help today.